Oh. I first encountered D about 2.5 years ago, and I think like most C++ programmers, for a long time I've had a love-hate relationship with C++. And I was attracted to D because it seemed to have given a lot of attention to fixing many of the gripes that I had with C++. And yet, the soul of why I liked C++, the soul of it, the essence of it, was still in D. And there was a second point of attraction, which was D seemed to be the first general-purpose language since Fortran that took numerical programmers seriously. I'm actually a physicist, not a computer scientist, and it's always seemed a bit scandalous to me that Fortran has still got this commanding position in the numerical world. There's been 3 decades, or maybe even more, of improvement in compilers, and the engineering world is still stuck with a dinosaur. But at the time that I first saw D, the D spec was quite defensive. It said that D aimed to provide 90% of the power of C++, but with half the complexity. There was a big emphasis on the bread and butter stuff, the array slicing, kind of. And but the flashy, weird, esoteric metaprogramming stuff, C++ could keep that. We don't want any of that. But somehow things have changed since then, and D has actually become a language where innovation is possible. And shortly after D 1.0, Walter added a couple of simple yet extraordinary features to the language. Now, I think Walter was in a bit of a mischievous mood when he put string mix-ins in, because there's really not much limitations on their use. So they're very dangerous. There is significant potential for abuse, but you can do some pretty amazing stuff with them. So this is the basic kind of hello world in metaprogramming. It's a combination of string mix-ins with compile time function evaluation. And the function is evaluated at compile time. In this case, it translates into a right-of-line hello world. And an interesting point about this is that the optimizer is not involved in this at all. This is purely done in the semantic and syntactic passes. This is possible because of the constant folding of strings. Having strings built into the language makes this possible, and I think that really vindicates that idea. If strings were purely in an add-on library, you wouldn't be able to do this. And this concept of textual substitution is an extraordinarily powerful concept. In the C language, it was the hash define, very simple text replacement. And when C++ sought to get rid of hash define, they came up with the template system. And even with the template system, that still doesn't cover everything you can do with hash define. In this extended with this combination of mix-ins and compile time function evaluation, that opens up significant potential for innovation. Consider one of the classic problems in computing. Well, linear algebra has been an optimization challenge since the days of the earliest computers. In numerical code, typically you have several vector or matrix operations in the innermost loop, and they really tend to be the bottleneck in an application. This needs to be fast. Typically those operations are very simple. For example, multiplying every element of a vector by a constant and adding it to another vector. That's actually a very famous algorithm. It's got the Fortran name of Daxby. And in the Olympic Games of computing optimization, that's the 100 metres. That is the innermost loop in an enormous number of programs. The Fortran solution to this is to create highly optimised routines for these operations. There's a set of BLAS, basic linear algebra system. And some of the core ones like this are implemented in assembler. In some ways, it's assembly language's last stand. And if you want to do an equivalent, if you want to compete with Fortran in numerics, you can't be worse than BLAS. But BLAS is limited. There's only a small set of operations it can do. Have something as simple as these examples up here. There's nothing in BLAS for that. So there's an opportunity to beat it there. Well, the natural way to do vector operations is to overload operators. Well, that gives ideal syntax. It always works. But if you're going to do something operating on built-in types, you can't create an operator overload for an array of doubles, for example. You have to wrap that in something. And if you just use simple operator overloadings, there's two problems. Firstly, you get lots of unnecessary temporary variables, and you get multiple loops. This example up here, adding these three vectors together, we've got multiple loops. We've got two vectors created on the heap, totally unnecessarily because they're deleted at the end. So the challenge is somehow, given that expression, A equals B plus C plus D, we just want to do a for loop and get that inside. There's a wizard solution from C++. Todd Veldhuizen, I'm not sure how to pronounce his name, the Blitz++ library. Also uses overloaded operators, but the trick that's used is that the operation is not done inside the operator. Instead, it records what the operation was and what the variables were. And this creates a syntax tree. You get a complex template. So for example, this A plus B over C plus D. You get multiple binary operations, varying the type. It's a simple concept, but it tends to make your eyes glaze over if you look at what's inside. Now, then when you finally come to your assignment, you make your for loop, And then this type has an apply method. When you call that, each one of those calls, it moves through the tree, and you get a mass of very trivial inline functions. It makes it easy for the optimizer to deal with. Hopefully, all this stuff disappears. But your basic point is, you got this expression on the outside, you turn it into a type, you put it in your loop, and you get the original expression back. It's quite reliant on the optimizer, and you can do the same thing in D. And in C++, this is the only choice you have. But I just get the feeling that when you're doing this, you're fighting the compiler. You've written your expression, you've turned it into a type, the compiler's done all this work to turn it into a type, and then you're putting it back in, you're untyping it and turning it back into your original code. So in D, it's possible to represent any vector operation with a single template, because we have both tuples and string arguments for templates. Now, the convention that I've used is uppercase letters corresponding to tuple members. So A is the first element of the tuple, B is the second, and so on. An interesting thing about this is that you can represent the same tuple member twice. So there's two A's in here. If you just do operator overloading, that information is lost. Yep. Yes, I will come to that later. And that's obviously preferable. Now, this is just as the previous one was the internal form, which the Blitz++ uses. This is the middle step. But as you can see, it's even somewhat usable in that form. Now, if you have a tuple of types, it'd be nice to find out which ones are the vectors for arbitrary types. Now, a simple way of doing that is it legal to add a square bracket 0 on the end of it? Can you index it? And I'd like to use that in compile time function evaluation. Unfortunately, there's a bit of a disjunction between the runtime and compile time reflection. So you can't use a index variable in a tuple in a compile time function. So this is a bit of a workaround. I create a Boolean array that has which ones are the vectors. It's really just the line in bold that's important. So then we have the non-wizard solution. Here I'm using compile time function evaluation and mix-ins. And what I'm doing here is exactly what you do by hand if you're given a vector operation and you want to put it inside a for loop. First, you put the for loop, then all these placeholder variables, the A to Z, you turn them into reference to the values array. I've got a point. If it's a vector, you add a square bracket I so that you're indexing the array. And that's it. That 20 odd lines of code gives you basic vector operations, vector scalar operations. Now what I like about this is that it's a direct representation of what you do by hand. So it's quite straightforward. And in this case, there isn't even a syntax tree. The compiler is doing all the work of parsing and semantic analysis. It can get a bit more complicated if you're having vector matrix operations, for example, just as by hand, it's also more difficult. I'll get to that later. But this gives us a nice start for adding some more things. For example, we can trivially check that every vector that you've provided is the same length. Just go through for all the vectors, assert that their lengths are the same. You can check that they don't overlap. Given the start of a vector and the length, just check that there's no overlap in memory. And most interestingly, we can do spot optimizations for cases of particular interest. For example, we can say, if it's A plus equals B plus C, B times C, and they're all doubles, then send it to DAXP. Then we have equalized with the BLAS. Therefore, there's no case where we're slower. But I'm not content with this. I'd like to do a bit better. We've got inline assembly in D, and I'd like to use it. Well, it's pretty hard to generate optimal assembly code. There's a lot of research to trying various things. But if you've got an algorithm that's known to be optimal, then you can tweak it a little bit and it'll stay very close to optimal. There's a guy called Agne Fogg who's at the University of Copenhagen, and he's the Pentium assembly world expert. He's got written a Pentium optimization manual, and he looks at DAXP in some detail. He's found all sorts of things about the Pentiums which Intel hasn't documented, and one of his triumphs was that when Intel first released the Pentium, to show off how good their Pentium was, they released some DAXP code. Agne wrote a faster version. So that's what I've started from. So I use the same loop design and the register allocation strategy that he's got. And it's a matter of plugging the calculations into the loop, applying a few design rules. And an important thing is that from what we did before, we have a general case, a fallback. We can go back to D. So now we just need to check, is this something we can do? Is this a case that's simple enough that we can generate our own assembly for it? And if it isn't, we say, no, we'll just fall back to D. on the Pentium class, we have the x87 floating point unit, which is notoriously difficult to work with because it works on a funny stack. It doesn't use registers like everybody else. But it turns out it works quite nicely in this instance. So given this, just do a few steps. Start off with the original expression in normal infix format. Change all the plus equals and minus equals, break them all up because they're not helpful in this case. And then change it into reverse Polish notation. Now, I'm not a Lisp guy. I was a fourth programmer in a past life, so I think postfix is more natural than prefix. But anyway, so it looks a bit weird, but it is. And then there's a couple of tricks with this processor. When you do 2 multiplies, the result isn't ready immediately. And if you try to use the result immediately, then the processor stalls. So it's better to do something else if you can. The things you can do are a bit limited, but one thing you can always do is when you have to add or multiply 2 numbers together, you can swap the order. So by swapping the subtrees, you can make sure that whenever possible, you're not using results immediately after they're calculated. And there's also a few other restrictions. If you're dealing with 80-bit floating point numbers, the reals, you've got less options for instructions, so you also add this into the infix conversion. Then when you've got that postfix string, it's actually really easy to convert it into assembly because you can do things in bits. So that example up there, BAD plus multiply, load C, add it, and store it. This is the innermost loop that's generated. In this case, I have C being a vector of floats, and the other ones are vectors of doubles. Normally in BLAS you can't do that. They only mixed mode operations. You're not going to get an optimized solution. But in this case you do, and as you can see, there's no junk in that loop. The loop counter stuff at the beginning, that's just 1 clock cycle. Well, since Pentium 2 and 3, there's the SSE extensions, which can do 4 floats at a time or 2 doubles at a time. And we can deal with them separately. They can't do mixed precision. A complexity there is you need to unroll all your loops to do 2 operations at once or 4. And that's a traditional register-based system. So it's much more standard. And if you want to get more modern and sexy, there's people are doing stuff using the graphical processing unit on graphics cards. Well, it's a bit of a hack, really. What you do is you pretend that your data is a texture, and then you ask the you ask the graphics card to draw it, and it's not actually draw it, and in doing these textures it does the results. Well, really, there's talk that some of the manufacturers are now talking about giving people direct access to that massive computational potential, but it's not there yet. Now, in all honesty, I don't have a GPU. I don't have a GPU that I can do this with. But it's a straightforward implementation of the same thing. But this is something that you really don't want to be built into the compiler. This is just too esoteric. Well, as Andre pointed out at the beginning, you'd really like to not repeat variable names twice. That a plus equals b times c is not perfect. Now, I don't think we can really do it perfectly at the moment. Perfect syntax sugar. We can do operator overloading, and using operator overloading generate the code, generate that single template. That has the same limitations as before. It still might be the best method at the moment. Something else we can do is use the mixin syntax directly. You get something like this. Now, unfortunately, you have this mixin and the open bracket, and you have the quotes. And it'd be nice to get rid of those. But it does let you do some nice things. You can do the alias detecting. You can give nicer error messages. And for small loops, you can unroll them in line without creating a template at all. And I'm hoping that macros will get us closer to this. Well, there's a lot of steps you need to do. If you've just got a string, you need to lex it, work out what the types are, resolve the aliases, convert the constants, work out the precedence and the associativity, and perform constant folding. Well, the lexing is not too bad actually, because in this case you just care about, is it a number or a variable name. And you can treat them quite simply. I think the lexa that I wrote was about 50 lines, and that covered everything. These next one, number 2 and 3, look really bad, but actually they're not. But the constant folding could really use some compiler help. This is how you'd, at the present time, without macros, this is how I determine what the types are. It's, once again, type-based search and replace. With the symbols which I've got from my lexa, I make an array with the types, get the string of that, that gives me the type, and I put the value itself, not string of, and that gives me the value. That does a remarkable amount of magic actually. That converts all the constants into, so for example, if you have ABC is a constant equal to 5, that translates it into the string 5. If you have aliases, they all collapse out. You can remove all the duplicates. Well, it'd be nicer not to have to do this, but it's not too terrible. The other one is determining precedence. Because you want to insert all brackets at the right places. Now, it's pretty tough if you have to go through and work out which has a higher precedence, string concatenation or multiplies? Well, I came up with this way of doing it, again using mix-ins. I just use the same trick from expression overloadings. I nicked this from C++. Wrap everything in a dummy class, and all that records is what the name is, whether it was A, B, C, D, or up to Z. And that's pretty much all I do. And then I wrap it in a type of, and then get the final .text member out of it. And then I send that, mix that in. Now when you mix that in, then the compiler goes and works out, well, what's the type of this thing? In doing that, it has to evaluate that thing that's in there. So it adds all the parentheses in. And in this AST class up there, I just record where the parentheses were, what order were things called in. And there it's all added in at the bottom. So mix in with A plus B times C times D, and it does all the work for you. Unfortunately, it doesn't work for everything. It doesn't work for relational operators, for example, because they have to return ints. So my wicked plan is foiled. But it works most of the time. Well, where does this all leave us? Well, the disjunction between runtime and compile time reflection is a bit annoying. And some of those steps with replacing, creating a nice front end, that could really use more compiler support. There's a big question of, with these mix-ins, they are probably a bit too dangerous. But part of my motivation here was to say, look, there's some really cool stuff in here, and we really want to, it's really worth hanging on to that. Don't want to lose that. But yet, we are at a point where we can create perfectly optimal code. And in a library, you can do optimizations that before you could only do in a compiler backend. Which is a very interesting place for a language to be. Thank you. Yeah. It's a little bit hard because many of these operations you don't have any Fortran equivalent for. What I made sure was that the code that is generated was identical, and I mean identical, to the code that's in the Fortran library. I haven't yet properly implemented the SSE2 section of this, but the inner loops with using the x87 for that's I think more than 5 times faster than a straight naive implementation. I'm sorry, I wanted to have a benchmark slide, but didn't get to it. Walter.
The macros with their syntax pattern matching could replace the mixins and make it a lot more powerful
On
alias detection of the point. Alias detection. So you have one like I think the previous slide was the slide before that. Yeah, so we have like resolve aliases. So
yeah. I'm only talking about trivial aliases.
so you're referring about just names,
Yeah,
replacing the names
yeah,
with the appropriate bindings.
yeah.
But in principle, if I think of it, we could generate code that at runtime is going to check for aliasing and fork into two different loops
Yep.
depending on the aliasing situation.
Yep. So, for example, if they overlap like this, if your storage is at the, it's exactly like a mem copy, a mem move. If it's going to overlap, if the one you're storing starts lower in memory, then start from that end. If it's the other way around, then start at the high end, so you never clobber it.
That's a complicated case. A simple time who does this in scientific computing doesn't deserve a gruesome death, right?
Yeah.
What people do is like this at the maximum. So they do alias the same. For example, like the dot product could be assigned to the one of the packets of the product was assigned to a whole new packet, and the code, the optimal code is going to be very different. So that's a great thing to do in
Yeah. Yeah, there's extraordinary potentials. Yes.
What were the particular extensions to drinks you were looking for?
Well, it might be directly via macros, but I could imagine something to given a string for the compiler to insert the parentheses for me. Especially some of this constant folding stuff would be good. Now, my answers to that question might change after we hear the end of Walter and Andre's talk. And so I'm kind of glad that they didn't get to that stuff in this. I think Walter's going to make a lot of this obsolete anyway. He's had a long history of doing that with my code. Some of what I think is the most brilliant code I've ever written. It was 500 lines of clever template stuff, and now it's down to 3. So I'm sure he'll do it again. But at least it's not obsolete now.
It makes it a lot easier after the fact.
Yep.
So I assume that the Athlon is going to benefit from the x87 optimization, but do you think there's any differences in the actual implementation that would cause you to arrange the instructions any differently?
Yeah, there are. Though actually some of the rules since for Pentium 4 are quite different to a straight Pentium. But in general, ordering of instructions is less critical because the processor does so much speculative evaluation and so on. Of course, when you've got so many more registers, as in the Athlon, it's much more, and the AMD 64, whatever, it's easier. Yeah.
Are you getting more and more routing cores? Now that we have standard with 2 and it's getting 4 and 8 and 64 that you mentioned there. Do you think you can benefit from the extension they were talking about yesterday in D with the what do you call native or pure functions to actually run things in parallel?
Could be. Yeah.
Is the problem in the access to the data, or is it actually computational power?
Well, in these kinds of operations, you would only want to do them on a single processor. But what you would have is, for example, these lowest level functions are normally called by matrix operations. And you split that up now, you might possibly want to do that on multiple cores. But yes, the pure function stuff is quite interesting for this.